In this example, we'll get some valuable experience about defining reference frames, which is a somewhat tedious but a really beneficial step that we have to do every time that we start a dynamics problem. And then we'll also find the vector derivative of this block as it's sliding down the inclined plane, and we'll do that in an inertial reference frame in multiple coordinate systems. So let's define our first reference frame. We'll call it reference frame I, which has an origin at O and the basis vectors E1, E2, and E3. Then sketch that frame on the drawing, and then add the basis vectors. We'll have E1 pointing in this direction, E2 pointing in this direction. E1 cross E2 creates a vector that's coming out of the page, and so there's our E3 vector. But we're not quite finished yet in defining this reference frame. We need to now define the orientation of each of these basis vectors, E1, E2, and E3. Now, and so let's start with E3. E3 is pointed out of the page as we've drawn it here, and that fits and is internally consistent with E1 and E2. And so to define this, we make it's a triple equal sign, which says that we're setting E3 equal to, and just write out of the page. And then next, choose the next basis vector. It can either be E1 or E2, it doesn't matter. Let's use E2, and we're going to define E2, and it's going to look vertical to us right now, but let's define it in terms of where the particle P is. And so we say that E2 is along OP when the point P is at the top of the ramp. And so what we're doing here is that we're setting our basis vectors based on real life, based on this actual system in which these directions out of the page, pointing out, and then along OP when P is at the top of the ramp, are tangible physical ways to define this, and they're unambiguous. There's no other way that you can interpret either one of these statements except for the way that we've drawn our basis vectors. And so then our next basis vector, E1, we then use the definition of E3 and E2 to define E1. And so E1 is equal to E2 crossed with E3. Now notice here that we didn't use the triple equal sign, which indicates defined as, but instead this is a mathematical expression where E1 is equal to the cross product of E2 crossed with E3. So now let's define another reference frame. We'll call it reference frame A, and it'll have an origin of O prime and basis vectors A1, A2, and A3. And we'll sketch it on our diagram. And we see that we have three basis vectors, A1, A2, which is perpendicular to that, and then A3. So now pause the video and try your hand at defining each of these basis vectors, A1, A2, and A3, based on the physical representation of our system. So pause it for a moment and try your hand at defining each of these basis vectors, A1 and A2 and 3, based on the geometry of the system and the locations of the points that we have already sketched on the drawing. The directions that I came up with were defining A1 as along the incline, but it's pointing downward along the incline. A3 being out of the page, just like we defined E3, and then A2 is the cross product of A3 and A1. Let's define one more reference frame to put on this problem. This is the reference frame B, and this frame is defined by this vector B1, which always points from the origin, point O, to point P. And so that'll be the first one that we define. So B1 is defined as along OP. So this vector B1 is going to track P regardless of where it is on the inclined plane. So if P is at the bottom of the plane, then that means that B1 will be pointing to what we're seeing as the right. So next, we define that B3 is out of the page, and then B2 is equal to B3 cross with B1. And we'll see a little bit later that reference frame I and reference frame A are both inertial reference frames, and then reference frame B is considered to be a non-inertial reference frame because it's rotating relative to an inertial reference frame. And now what we want to do is we want to take the time derivative, which is a vector derivative, of this block that's sliding down the plane. And so we have to start with our position vector. So we have r of p with respect to o. And we can define this in multiple ways. We've put lots of different reference frames on here. And so let's start with a Cartesian coordinate system. And with the coordinates x and y, we're able to define the position vector as x in the e1 direction plus y in the e2 direction. Now if we write this in terms of our b basis, we have the b1 vector, which is always pointing from o to p no matter what. And so we need to have a distance, and that can be r, just as if we're using our polar coordinates. And then we would say that the position vector p with respect to o is r in the b1 direction plus 0 in the b2 direction. The last frame that we see is the A frame, in which A1 is moving down the plane, or pointing down the plane, and A2 is perpendicular to this. And so if we use our coordinate S, which you're already associating with the path frame, then what we see is that the position of P with respect to O is equal to O to O prime and then O prime to P. And so from O to O prime, it's the distance h in the e2 direction plus the distance s in the a1 direction. And so let's take our first one that's in Cartesian coordinates, and so the velocity of p with respect to o as observed in the inertial reference frame will be x dot e1 plus y dot e2. And then the acceleration of p with respect to o as observed in the inertial reference frame is x double dot e1 plus y double dot e2. If we decided to use polar coordinates with this and still keep it in the e1, e2 basis vectors, then we replace our r, p with respect to o, and we replace the x as r cosine theta in the e1 direction plus r sine theta in the e2 direction. This position vector is already expressed in a basis that's fixed in the inertial reference frame, so the time derivative in the inertial reference frame is simply the time derivative of the scalar that precedes the basis multiplied times the basis in each direction. And then to calculate the acceleration of p with respect to o, we take the time derivative of these scalars and keep the same basis, e1 and e2. And so you can see in particular with the expression for acceleration, although it's pretty easy to calculate, it really doesn't give us a lot of insight into how the block P is actually moving. And so by choosing polar coordinates in this case, it doesn't give us a lot of insight to the motion and can actually be a little bit cumbersome to use. So let's move on to the time derivative of the position vector when it's expressed with the b basis. And so we're still calculating this as the velocity of p with respect to o as observed in the inertial reference frame. And so we take the time derivative of our scalar and multiply it times the basis vector, so it's r dot in the b1 direction, and then we need to add to this r multiplied times the time derivative in the inertial reference frame of the b1 vector. And so here we run into the roadblock that we introduced in the last screencast, in which we have a scalar multiplied times a time derivative of another basis vector. And we haven't yet worked out the tools that we need to calculate the time derivative of a basis vector. So that's coming, and we'll be able to finish this in a future screencast. So let's move on to the last reference frame that we have, which is reference frame A. And recall that when we used reference frame A, we used the path coordinate in the A1 direction, but we had to combine that with a distance in the other basis, which is in E2 direction. And so when we calculate the velocity of p with respect to O in the inertial reference frame, we take the time derivative of the scalar and multiply it by the basis vector, and this gives us h dot in the E2 direction, and we add to that s dot in the A1 direction. Now, h is a dimension, so that means that h dot is equal to 0 because it doesn't change with time, and then the acceleration, p with respect to O as observed in the inertial reference frame, is s double dot in the A1 direction. Now you can see these are very simple expressions for both the velocity and the acceleration of p with respect to O as observed in the inertial reference frame. And these were made possible by two things. The first is that the basis A1, A2, and A3 is in the A reference frame, which is an inertial reference frame. And so we were able to use these time derivatives, and they went to 0, just like the E1, E2, and E3 time derivatives did. In addition to this, we chose a path coordinate, which was the distance in this case between O prime and P, and so we had a well-defined path, and so we ended up with a simple expression of s dot and s double dot, which also is the only way that we've defined this that's reflected that this is a single degree of freedom system. Look back upon the expression in Cartesian coordinates with x and y, and we end up with an x double dot and a y double dot in the E1 and E2 directions. And because this is a single degree of freedom system by observation, that means that we need to come up, to solve the kinematics fully, we need to come up with a constraint equation to take these 2 degree of freedom system down to 1 degree of freedom.